Good morning, everyone.
Good morning.
Good. I'd like to introduce you to Harold M.H. Chong, who is an associate professor. He's from the faculty and the Department of Electronics and Computer Science. So if you could welcome him, please. Frank, record. Oh yes, sorry. You started. Okay. Alright, sorry. Just ignore me. Okay. Okay. No, my apologies. Okay. Well, thank you. Thank you, Frank. And this is my first opportunity to give a lecture. And good to see a room full of students. And hopefully you learn something from me today. So, as Frank introduced me earlier, my name is Harold. I'm from the Department of Electronics and Computer Science. And so I teach there. Okay, I teach in subject of semiconductor devices. And on top of that, I'm also doing research. Okay? Research in semiconductor devices. And besides that, I'm also the director of the clean rooms. So we have a big lab in Southampton, and where we actually fabricate the semiconductor devices. Okay, so what you're seeing here is Southampton is a very unique university. Unique university because we not only we can think about semiconductor devices, but we can actually make them, measure them, and understand them. Okay, so this is a very unique opportunities here. So, but first thing, what I'm going to give a lecture on it will be semiconductor devices in everyday life. So before I start, I'd like to ask you a question. All right. How many of you own a smartphone? At least one. Don't be shy.
Yeah.
I think nearly everyone owns a smartphone. Good. How many of you own a laptop or personal computer? Pretty much everyone. Good. Right. How many of you has contactless gadgets? Slowly, okay, because contactless gadgets starting to come in. All right. So the last question. How many of you, sorry, let me rephrase that question. How many gadgets do you carry every day? Electronics. One or two. That's good question. Good answer. Any more? A lot, yeah. Maybe two is the max at the moment, but without you realizing, it actually could be more. Okay, more than two, because your gadget is interacting with other gadgets without you realizing it. Yeah. So this is why I'm going to talk about it, because these are because semiconductors, they are ever present in your life, just like the air you breathe. All right. So why is it so important? So I'm giving you an outline of the lecture today. I'll give you the background of semiconductor devices. Maybe I'll just rephrase it, what are driving those electronic devices, those gadgets? You may want to ask, what is semiconductor materials? Why is it so special? A bit of history. I love history, especially engineering history. Okay, and to look back, who has done what in the past that actually we are benefiting now. And we'll look at an example of semiconductor called silicon. Okay, and we'll look at the operation of the silicon transistor. Okay, and what is the future hold for us? Okay. Now this is a schematics of some of the example of semiconductor devices to start off with. Now, where can you find semiconductors devices, right? These are not the only example, there are plenty more, but you will find electronics devices which are semiconductor based in aeroplanes, yeah? Electronic gadgets. I'm sure everyone owns these too, yeah? Automotive electronics, the safety, because cars are getting more and more electrical, okay? And which means that they are getting, it has more and more computer on board. Now, this is a report published last year by IEEE, the Institute of Electrical and Electronic Engineers. They said on board of a car there are at least an equivalent computing powers of at least 30 computer servers to operate the car, or for 30 PCs basically on board of a car. It's a lot of computers, but you don't see them. They're hidden away. But those computers actually make your driving experience pleasurable, and as well as keeping you safe. Alright. There's also integrated sensors, okay? Sensors for everyday life, healthcare, environmental sensors. So those are also based on semiconductor devices. And lastly, that will be the future, smart home, okay, or smart building. Now we're getting so used to everything being smart, so the very first thing we enter a building these days, besides asking where's the toilet or where can I buy coffee, the third question maybe you ask, is there any Wi-Fi? Is that correct? Yeah? And I want Wi-Fi. That's why. You want to be connected. You want to be connected with your devices. Now let's look at connection then. What are those devices and how can they interact? So this is looking at the different years, right? So we are the end users. If you look at this graph by Stifel, yeah, and then you have the property. So this is for the business people. So we're not, as an engineer, for now I would like to make money, but not for now, because I know my technology and my research is still in the early stage. But who are the world leaders in those type of technologies? And what are those devices? So you probably can, before even seeing what this graph looks, what is this graph about, you already notice some of the brands easily, isn't it? Those brands, for example, this one, Google, yeah, Apple, Facebook, Twitter, etc. You know this one?
No.
Well, maybe it's not. That was my time. All right. That was when internet was very, very, very slow. It takes 10 minutes to properly load a website. I'm not joking. And that is called Netscape. You heard of Netscape? So it went bankrupt many years ago because of Google. But you see how technology evolved together with the applications concerning you. So which means that we as end users, we are connected to billions of or trillions of connected devices. Not only the two gadgets you are carrying with you, but you're connected to other people potentially because of these enabling softwares. Yeah? And so now we are here, 2015 or 2016, 2020, for the future. You can see there's a new word called Internet of Things. Alright. And this Internet of Things, which I'll go to the next slides, explain to you why these electronic devices based on semiconductor technology is important. Okay. And finally, I love to ask this question to students or to the public. When is the last time you delete your data in your hard disk or your pen drive or your cloud? Long time ago. Excellent question. Ever delete your old data? Never. Most of the time, okay, except for bad pictures, bad holiday pictures. Yeah, of course, or forgettable experience, you can delete them. But you always keep your data, isn't it?
Yeah.
And you keep it more and more. And once your cloud storage gets filled up, you ask for another 1 terabyte, isn't it? And you keep asking. You never delete. I'm the same. I have my Dropbox. It's already full. And Google, I can't remember, Dropbox, every week emailing me said your Dropbox is full. Your Dropbox is full. Please upgrade.
Back up.
Exactly. Because we never delete or we never back up. We keep storing. It's human nature.
Yeah.
And where do you think those storage goes to? It's not to the real cloud, but it is actually to the actual solid-based materials that store your data, your memory, basically. Your memory. Which means that, and those memory and those type of devices is based on semiconductor technology. Right. So this is a report published, I think early this year. It's called the Internet of Things. Don't know if you can see it properly, but this is from Intel. What Intel is saying that, well, this is a very poor image. Do apologize. Okay, take 2015, yeah? What it says here, 15 billion, it means 15 billion electronics devices. It's actually your gadgets that is been around the world. What's the population of the world? 7 billion, roughly twice. So you are right, those who answer at least on average, one person owns 2 gadgets is correct. Well done. So that's 15 billion of them. Now, by 2020, which is in 4-year time, it's going to explode to 200 billion. Yeah? Because, like you said, cloud, memory, we don't back up, all those is going to take hold. Because everyone's starting to use technology. Okay. Now, this is Intel prediction. They say you are always surrounded by at least 26 smart objects in everyday life. Is that true? So this is some a good example. PC, games, of course. You play a bit of games. Singing, karaoke, your phone, your health monitor, yeah, your music, home, watching movies in YouTube, okay, cameras, shopping, contactless car, everything. Now, if you think like, what is watching movie has concern about me in the gadget? Well, actually, you need a device to operate and watch your movie. You see, so which is actually makes sense. I actually counted. I was in my office a few months ago. I actually surveyed my surrounding of my office. It's not quite 26, but at least it was 15. Yeah, because I forgot them to 15 because it includes these sensors, these smart sensors, protecting you and keeping you safe. Okay. Now, I changed my sentence from what is to what are driving those smart devices, yeah, or smart electronics. It's actually semiconductor devices. Okay. Now, let's take a closer look at what is semiconductor devices. But before we look at those devices, let's understand what is it made of first. Yeah, what's the key ingredient? Let's look at the semiconductor materials. Periodic tables. Everyone familiar with periodic tables?
Yeah.
Very good. Okay, and I'm assuming everyone has a science background. Okay, good. Now, I never remember my periodic table. God honest truth. Okay, but what I remember is the groupings. Are they metal? Are they gas? Are they? What's the third one? Liquid. Of course, yeah. The three state. Yeah. Gas, liquid, and gas. Gas, liquid, and liquid. Gas, liquid, and solid. Solid. Don't forget. Right. So, but in this in these periodic tables, what's interesting is there's a group of elements. Yeah. There's a group of elements that does not behave properly, meaning that it doesn't behave properly like metal, although it looks like metal, or it does not behave, for example, it does look like a insulator, which means does not conduct electricity, and then suddenly, when you apply a voltage, it does conduct. And these type of metals, I would say, they are unsure of themselves. Okay, and it needs help to become something. So this is very important properties. Unlike proper metals, like metals exactly, you conduct electricity, yeah, or gas, it's gas state. But this kind of materials or elements tends to belong in this area. Okay, in this region of the periodic table. Now, if I take out of that periodic table, see the shaded area in orange? Those are the type of elements that what I explained earlier. The elements that are not unsure of themselves, which actually the elements that need help to change its state. Yeah? So, now this letter looks familiar to you. You have aluminum, silicon, phosphorus, sulfur, copper, zinc, gallium, germanium, arsenic, selenium, telluride, antimony, indium, cadmium. That part I remember. Okay, because that's my job. Okay, that's my work. So, but one element that stands out, from the rest. Can you guess which element is it? This one. Out of this shaded area. Silicon. Excellent. Good question. A good answer. So, right. So what I'm going to talk about more is silicon today. Okay. Now I'll explain to you in a minute. Now when I pick silicon here, the next thing, a host of questions start to arise. What is silicon? Why is silicon semiconducting? Where can I find silicon? How does it work? Everything, all the questions that you're always asking. Okay? What? Where? How? Why? Yeah? Those are the typical questions that you always start off. Yeah? Now let's look at these questions one at a time and help us understand how can silicon help to drive all those electronic devices. Before we start, let's go back to history. Now this is, you can see the year change until 1969 here, 67. Now, I did not include the year before because I'm going to concentrate mostly on devices. Okay? Now, in actual fact, in 1833, about 40 years back, Michael Faraday, you heard of Michael Faraday? Yeah.
Yeah.
He discovered semiconductor effect. in his experiment. Okay, because he was measuring a piece of metal, copper. He was measuring conductance. He has no fancy equipment, and he was measuring the current passing through, and he's happy. And then he got a piece of material, which is in his mind is like semi-metal, but he wasn't sure that how he will conduct the electricity, because that was his research he was doing. And then what happened then is when he tried to measure it, there's no current passing through, or there's no electricity. Then he switched on the light. Suddenly, the current passed through. Switch off the light, no current. And he wrote in his logbook, in his journal, he said he was actually recording, observing this phenomena. But you're talking 1833, they don't have fancy equipment to make devices. So after that, he never went on to research into making electronic devices. But of course, he became famous for other things, like the electromagnetism. So, but 40 years later, a brilliant scientist called Braun from Germany fabricate or made a device called point contact transistor. What it means is he actually made a very, very crude integrated circuit. You're talking Victorian time, more than 200 years. Impressive, right? So that was the very first transistor, I would say, or a diode device. And he observed a rectifying characteristics. You heard of diode before? Rectifying means there will be a moment in time when you apply the voltage, that the device will switch on. Below a certain voltage, it will remain off. All right, now you understand. That was discovered more than 200 years ago. Very clever man, isn't it? And we're still studying it. Unfortunately, Braun, I think he set up a company, and now his company now stopped making blenders and vacuum cleaner. So no, so more for consumer electronics. But 1907, army engineer, a British army engineer. He's not even a scientist. He discovered LED. Okay, and you are using LED now every day. Your smartphone, the display is LED, but that was discovered in 1907. As long as that, 1920, the 1920s are the best year of semiconductor devices. I'm quoting 1 year only, but throughout the 1920s to the 1930s, a lot of discovery has been made, including Einstein discovery as well, which I did not include here because I'm biased. These are all mostly engineers. Einstein is physicist. All right. So I'm an engineer, so I support my engineer fellows here. So you have the first transistor, and then slowly you can see silicon PN junction now. Those diodes, which I explained to you earlier, that was actually used in the 1940s, and it was first used during Second World War. Semiconductor devices as part of the electronic device gadget they were using those days. As the year went on, you can see now transistors start to get hold on. 1954, solar cell by Chapin, Fuller, and Pearson. This is actually a picture of the advertisement in the 1954. They actually advertised to family to buy solar cell. Okay, and they are still trying to get you to buy solar cell. Way back. So you're talking nearly 60 years, more than 60 years ago. Why is it so bad? Why don't we buy more solar cell? There's a lot of problem. Problem can be due to the semiconductor device technology was not mature well enough those days. Then you have more transistor, and then more than 50 years ago, another LED. Now this time, much better LED, lasers in 1963, and then memory devices. So you can see the progressions of the discovery of semiconductor device throughout those years. And after that, you have integrated circuit, microchip. Okay. And Southampton, actually, I did not put here, 1969, Southampton, this university, demonstrated in the university level that you can actually fabricate integrated circuit on a semiconductor material. So together with these famous people at that time when they are still alive. So this is the background history to Southampton. Now, after that, let's look at the material of silicon. Next question is, where can I find silicon? Actually, you find silicon everywhere. Sand. Silicon is actually the key ingredient of sand. The raw material is from silicon. Yeah, from glass windows. Yeah, glass windows is actually made from silicon dioxide. That is the part of sand. Now, of course, you have to purify the sands because it has a lot of other minerals. Those minerals give this color. Now, a pure sand color. Have you ever seen white sand before? White color. Powdery. Never? Maybe I'm the luckiest man in the world. In my country, there's an area in my country. It's next to the beach. It's actually white sand, and I used to play around it. And I just wonder, when I was young, what is that white sand? I thought someone accidentally, the talcum powder. I thought someone accidentally dumped a talcum powder in the beach. But it's actually turned out to be, it's pure sand, pure of all the mineral. It's actually very close to powdered glass. So if you take your glass, you grind it, it will be like that. Okay. So you take away all the minerals, what you left is powdered glass, white color. You purify it further and you melt it and you crystallize it. Okay? Now, after melting, when you recrystallize it, it becomes this ingot, we call it. Ingot is like a high purity crystallized silicon. Okay? And what they are doing here, these engineers, they are actually sawing, they're slicing the crystal. So what you're seeing here is it's a giant crystal of material, like your crystal, like in your diamonds, crystal like in sapphires, yeah, all those precious gems. Okay, but of course, silicon are not that expensive as diamond, yeah, but it has the same kind of crystal lattice structure. Now, when they slice this, what you have is this type of wafer, what we call wafer, and you start to build your electronic devices. And this becomes your microchip. Unfortunately, in my hurry, I forgot to bring all this. They are all in my office, so you can actually see it in yourself. But if you have the opportunity to go to the clean room in the future, you will be able to see some of the examples here of this type. Now, they come from sand. Now, the next thing is why silicon is semiconducting. Now, we're going to a bit of physics. I'm not going to go into detail. If you take my course in the in your first year degree or second year degree, you learn a little bit more about this. Now, in a crystal structure, you learn in school, when you have crystal, means that you have atomic lattice, isn't it? The atoms are arranged. You remember though. Arranged, for example, in order. Yeah?
Mm-hmm.
They are arranged in order and they are bonded. Bonded means they are glued together by what we call covalent bonds. It's a special force. They are glued together by a special force called covalent bonds here. Now, the term of silicon, and on top of that, silicon has 4 electrons around it. Okay? There are 4 electrons. So those 4 electrons, so the 1, 2, 3, 4, 1, 2, 3, 4, yeah? They glue each other. Okay? Now, because of those periodic structure, and because periodic means the order crystal lattice, and because of those electrons, what you see, it has a special energy. Yeah? So if you plot an energy diagram, so you're going to measure the energy property of the materials, for example, what you get is a special graph called electron energy graph. Okay? At the bottom end from 0, yeah, if you're plotting a graph, you start with 0, your origin, and this is my length here of the lattice. What you see, an energy region called valence band, which is full of electrons. Full of electrons in the at 0 Kelvin. Not okay, yeah? Sorry. Alright, at 0 Kelvin, meaning the lowest of the temperature. So imagine that you can go to that cold, very cold, everything stands still. Alright? When everything stands still means then all the electrons stay with the silicon. Then, if you keep on measuring, you find there's nothing here, what we call band gap. There's no energy. Right. And separating that energy we call a conduction band. As another energy level suddenly appear. That energy level is conduction band but empty. There's no electrons there at 0 Kelvin. The reason why I put 0 Kelvin here is I want to start from nothing. Now as it goes to room temperature, which means how much is room temperature? 20 degrees Celsius, which is roughly 273 Kelvin. Okay? Now because of that temperature, these electrons start to have energy. And this energy would allow the electrons to move. That's why it's conduction. When you think about conduction, and I know some of you get confused with this graph, is it no electrons, but it's called conduction band? Well, it does conduct. Only when you apply voltage or only when you are at higher temperature state, because you want the electron to move. That's why it's and you will conduct at this region. Okay. Now this property, yeah, when you think about it, you remember what I said, some of the material are unsure whether they are conducting or when they are metal or not, and that is due to this graph here. Okay? And these are very unique. Not all elements in the periodic table has this. Okay? Remember, yeah? Not all of them. And those elements I showed you earlier, they all has this. Yeah? And that's why the semiconductor devices, when we're making them, we can only use this group of materials. Okay? And this group of materials goes on, it also applies to the Like, for example, when people are mining, they are mining for this material as well. Okay, so we currently, as a scientist's prediction, some of the elements can only last for 100 years, 2 more generations, roughly. Some, like silicon, which is much better, there's sands everywhere, so it lasts almost indefinitely. But some of the semiconductor elements have limited resources. So in the next 100 years, I don't know what type of semiconductor devices it will be. All right. Now this is what I explained earlier. Conducting means that you have electron flow, you have current. Insulating, it stops. So these are the type of characteristics. Basically, it's like a switch. Now this is what I explained to you. Now if you pure silicon, what you have is those band gap. But on this pure state silicon, it doesn't know whether it can conduct or not. Okay, so you have to help it. You have to help the silicon to achieve those conduction. And to achieve that, you start to put in other impurities, other elements to the silicon. So if you put arsenic here, okay, what you get is a negatively charged silicon, N-type, what we call. Now if you put boron, it's another element, into the silicon, you replace the silicon away, you look at the image, you get a positively charged. And this is called holes, because you're removing the electrons, the red dot. Here you're introducing an extra red dot, which is extra electrons there. So making negatively charged material and positively charged material. Now we all know electricity, so if you look at the circuit diagram, in electricity there's always plus and minus, isn't it? Yeah? Plus and minus, that is where you have your electric field and help to move the electrons. This is exactly what we are trying to do. We're trying to establish those plus and minus in the material. Okay? And this is the key ingredient for making electronics device circuit. Okay. Now how does it work? I deliberately jump into the device, the real device level. What you're seeing here is a cross-section of a silicon transistor found in your microchip. Alright. This size, this square block here, this dark square block, is about 30 nanometer. So this is, you take a meter, you chop it 30 billion times. That's small. Guess what? We can fabricate in Southampton this device. Okay? We can fabricate this type of device. So that's small. What you have is, you remember the negatively charged material, positively charged, negatively charged. So this is what we're trying to establish here. Now what we want is, this is the source, this will help the electrons, source of the electrons, and this is drain. It means we are draining the electrons away from the device. So when we apply an external voltage to the top, what you see here, we're going to form a bridge. Yeah? Before that, the electrons cannot pass through because there's an opening. Now we're going to form a bridge here so that to allow the electrons to pass through. And then you remember the red dots of electrons starting to appear and it can cross. And this arrow shows the current flowing. Now this is meaning that your circuit is fully connected. Now let's look back to the circuit diagram. I hope you're familiar with circuit diagram before. Looks familiar? So this is a standard circuit diagram. You have the light bulb, you have my voltage here, another voltage, but this is open circuit. The circuit is not connected. Now if I apply the gate voltage, it becomes closed circuit. So this is what we call the channel. Remember that connecting bridge? And what happened then, the red is the flow of the current. Yeah? So that's actually nothing but a switch, a transistor. A transistor is a switch. Now, let's look at a different circuit. If I switch on and off, if I switch on and off this gate voltage, I get a pulse output, isn't it? Yeah? Guess what? It's none other than the 0 and 1 of individual transistor switching on and off 0 and 1. And those 0 and 1s are the data, your data, your memory. Yeah? Now, this is what it actually looks like. Remember the transistor? It's actually a cross-section of single transistor device. From this cross-section of a silicon chip actually come from this wafer, come from the Intel Xeon. You've seen it in your computer, or Intel Core, Quad Core, whatever, yeah? Actually come from the motherboard of the PC. Then eventually goes into here. There are billions of them. In these chips, we're talking billions of transistors. Yeah? And those billions of transistors are switching like what I showed you, 0 and 1, 0 and 1 all the time. And that creates those data, that creates your internet web browsing experience. Okay? All because of this one guy, this one transistor here. Okay? You must love this transistor. Okay, everyone owns this. Right, so I'm going to finish soon. Let's look at the evolution of electronic devices. I was in a museum a few years back, and I saw this fantastic computer. It's actually a PC, 1965. This round disk is actually tape, magnetic tape, and that's actually memory. This size. So imagine you're carrying a memory this big around. Now we are carrying memory with a memory sticks this size. And this can store more than 100 of this. Alright. Then the 80s and 2000s, we have a PC like this at home. But now we are carrying this a lot, isn't it? Tablets. As powerful as the home PC these days. Mobile phone, 1973 to 1984. I remember using this. It's 2 kilos. This guy weighed 2 kilos. Not joking. By Motorola. This is the first mobile smartphone, you can call it. It doesn't do text. Only phone call. But the technology went back to 1942, Second World War. Motorola actually made the army walkie-talkie, and they used the same technology, the design to save. But 1992, because the battery only lasts, a good 45 minutes or less talking, yeah? So they invented another mobile phone. Actually, they make it bigger because the battery is about this block, yeah? Really heavy, nearly 4 kilos. Right. Now you have your Samsung, your Apple, or LG, whatever, Xiaomi, you have that. So you see how it changed, all because of those transistors. keep getting smaller and smaller and more powerful. Now the other thing is, we also make gadgets bigger and bigger. Then those gadgets are supercomputers. Those supercomputers, this is actually a giant calculator. Supercomputers, nothing but calculators. All right, servers, yeah. So this is in the 1960s. Now you have this IBM Blue Gene. I don't know what it means, Blue Gene, but this is a supercomputer by IBM now. And everyone in the world are building some supercomputers. Give you an example. This is from China, the Tianhe 2, the application here. This is, I think, the latest. What are supercomputers good for? You may ask. Like, why are we bothered? Yeah. Why are we interested in making our transistor faster, smaller, and more powerful? Because we want to build better computers. But what is computer for? Actually, studies of quantum mechanics. Yeah, understanding of the new physics. Fluid dynamics, design of new cars, engines, yeah, aeroplanes. Weather forecast. Actually, we use supercomputer to predict weather forecast with great accuracies these days. I remember 20 years ago watching the news. Actually, the news presenter said tomorrow will be raining. Hopefully. I'm not joking. That's what they said. Because the prediction there is almost 50-50 accurate. Yeah? But now they said tomorrow is going to rain, and I guarantee you, and true enough. That's because of it. You have study of the universe, the Big Bang Theory, not the TV. Yeah? Molecular modeling, right? That DNA to make better drugs. Yeah. For pharmaceutical application. And finally, they're good at playing chess. Yeah, that's what every time you hear a new supercomputer came out, yeah, they said they will always test it in playing chess. Okay, but this is the least use of supercomputers. Now, here's some anecdote for you, a story. This is a computer server's farm, okay, or data farm. Right. And this is Google data center in Lenoir, North Carolina. This building, this outside here is the air conditioned. This building inside is this, and each of these are servers. Servers, Google servers for you. But there are not only one of them, there are many of them around the world. So if you perform 2 Google searches, you do, okay, I can recommend you the first search, you can search for me. Alright. If you do 2 Google searches, is equivalent to the power to boil a kettle, to make a cup of tea. That's the amount of energy needed. Yeah? And this is actual. These facts came from Google themselves. Google, yeah, if you don't believe, you Google it to Google it. Alright. So it's quite not surprisingly that they need these air conditions, power supply, to power those servers, to power those tiny transistors, to service all of us. So what's the future? I don't know, there's only 2 things I can think of: the Internet of Things and the smart connectivity and communication. Basically, like I said earlier, all our equipment and our gadgets are connected. Everything is going to be smart. Okay. So there's a famous scientist that he said eventually human, we are in the end a walking computer. Okay. With that, I thank you and I welcome you to Southampton again. And this is where it all started, fabricating devices since 1969. This is building. Any questions?
I think they have lots of questions, but I think they're just worried about getting to the class.
Oh, sorry.
No, that wasn't...
Sorry, I overran by 5 minutes.
No, it was fascinating. I think that they have questions, but they're worried that if they ask, that they'll get told up.
Fair enough. Okay, I hope you get you learned something today from me. Please.
Perhaps if they do have questions, if they have to contact you, is it on the first slide?
Yes. I will upload it. I'll send this to Megan again because I sent her